So I would like to invite the second invited speaker, Jūras Banys, and the presentation will be microwave spectroscopy of ferroelectrics and related materials. So please.
Great. So, dear ladies and gentlemen, first of all, I would say a few messages. The first message is thanks, organizers. It's very great to be here in Palanga and to give a live talk after 2 years, more than 2 years of pandemic. We are getting used to the screens, watching the screens, and this is actually the solution which helped to keep the contact, but it's much more pleasant to see the faces, to see the people, and to have the live discussion and to meet the persons face to face. Second message, not the pandemic only. The pandemic is nearly over, I hope. It will finish, but the war in Ukraine, the Russia aggression, it turned again huge challenge for whole world, and whole world now is united. And I hope that Ukraine will win against aggressors, and democracy and freedom will remain in Europe. And the third message, again, thanks to organizers, I got the invitation, and it was the huge challenge for me which topic to choose and what to talk, because the title of a conference, as you can see on the screen, is electronics, and I should talk about electronics at least, if it is electronics conference. So what to do, what to speak, and I decided to talk about microwave spectroscopy, because when you go into the street and ask any person on the street here in Palanga, what is electronics, the first thing what he will do, he will grab into the pocket and show mobile phone. This is electronics. Not only power lines, what the first speaker was talking about, and I'm very thankful to the first speaker who mentioned such a term, modes, because I will be chatting about the modes as well, but only from, I guess, different modes and different systems. So when you have electronics like mobile phone, radars and similar stuff, you use a lot of equipment, not only resistors, transistors, diodes, and so on, but also you use capacitors and another smart materials. And in electronics, in mobile phones, now we are going to 5G, and the frequencies are increasing. Computers, also due to the computers, which are getting faster and faster, you need to use another materials. And when the frequency increases, you need to know the properties of the materials which you use. Also, I looked at the program, and there are several talks about PVDF, about energy harvesting, piezoelectric materials. And also, this properties of these materials are also very important, because before making efficient schemes, fast working schemes, you need to know properties of materials at different frequencies. So I will introduce a field which is material characterization in a high frequency regime. So first I will give short introduction, and then to characterize these materials, you need to have some measurement methods. And especially when the frequencies are going up, measurement methods are getting more and more complicated. At extremely high frequencies, they are more simple. So I will try to show that, and the measurements at microwaves, at high frequencies, you use different methods. So instead of using simple capacitor, In electronics, usually they are used capacitors, which are based on barium titanate. But at higher frequencies, the electric materials, they have the electric dispersion, properties are changing, and how they are changing, how they do that, you need to know. So first, you should use coaxial line, and higher frequencies, you should go to waveguides. So it's X band, Q band, and W band finishing. And I will show some examples of materials, and at the end, I will give the conclusions. So if you look at the electromagnetic spectra, you have, sorry, this is in German, because I took it from internet, very simple. So if you have the long waves, which are kilometer long, so it's radio frequencies. If you go to higher frequencies, it's telecommunications, mobile phones, microwaves. You end with terahertz, and from terahertz, you go to infrared light. And from infrared light, if you go ultraviolet light, and then you go to Röntgen or X-rays. But everything is electromagnetic wave, nothing else. And for example, microwaves at about 80 to 100 gigahertz, it's very important. Just today in the morning, drinking coffee at home and looking internet, I got the message, I found the message that Sony and Honda are planning to establish new car company, which be cars without drivers. And you know, cars without drivers, they need to have radio location, because otherwise they cannot find where the street is, the tree, the people crossing the street, cats, and so on. So there are a lot of radars in the car. And these radars are working in the frequency from 80 to 100 gigahertz. And these radars, of course, will be not outside the car, it will be inside the car. And it's a huge problem from which material to make outside bumpers, sides, and so on, which do not absorb microwave radiation or have very small losses. And I can tell the small secret, we have with one Japanese company contract and measuring materials exactly in that frequency range, choosing which material will be the best for these cars. So then we have electromagnetic spectra, and you have some material which you want to use in the car or in the mobile phone. You need to know the properties. So what I mentioned, it's electromagnetic wave. And I will tell nothing new to you. Already in 1863, James Clerk Maxwell wrote equations. He wrote more, it was 5 or 6 in the beginning, but finally, electric and magnetic fields can be fully described with these 4 differential equations. Of course, it can be in integral form, it can be in differential form, but this explains everything. And you put different boundary conditions and you get all the information. So at this point, my lecture can be finished. You got all the necessary information. It's fundamental laws, it's true, it's working, and very nicely. And mobile phones, everything. TV, radio, and due to the war in Ukraine, also guided missiles, and so on, everything works on these equations. So, another issue, then we have a material, any material, the electric material or ionic material, because it will be also so in the program, few talks about batteries. So if you look at the frequency range, if we start from the low frequency part, in the low frequency part, we usually have a conductivity processes. This is a charge transfer, which is going from one contact to another. Then you apply electric field, and if we have ions or electronic conductivity, we have a conducting material. So resistors or water, ionic liquids, ionic conductors, which are used in batteries, lithium batteries, for example, they have ionic conductivity. So it's one big field also which investigates ionic conductivity in ionic superconductors. And this is for batteries. But usually this is finished at about kilohertz frequency or megahertz, depending on the level of conductivity, on mobility of ions. And at higher frequencies, at microwaves, you have dipolar. For example, water. Water H2O have a dipole moment, and water, the static dielectric permittivity have around 80 here and around 8 only here. So it's a huge drop, and it's so-called Debye type dispersion when the dielectric permittivity decreases. And of course, real part when decreases due to Kramer's chronic relation, we have a change in the imaginary part of permittivity. So red curve is the dielectric losses or imaginary part of permittivity, and blue one is the real part of dielectric permittivity. If you go further to, to infrared or high frequency microwaves, you have atomic vibrations, polar vibrations, because in the crystal lattice you have modes, vibration of atoms, and they are transversal and longitudinal, and transversal polar modes interact with external electric field, and you have absorption, and this is so-called resonant dielectric dispersion. And you have such a peaks, it's shown 1, for example, but in complicated materials, you will have a huge bunch of them, whole set. So infrared spectroscopy, for example, is used to trace the drugs due to characteristic lines. And further on, if you go close to Röntgen, you have electronic polarization, and then the electric permittivity is equal to 1, and whole dispersion is finished. So this is how it looks like the behavior of the electric material at high frequencies. And once more, before using the electric material in electronics, as a capacitor, for example, in computer, or strip lines and so on, you need to know properties of the material. So now a bit of advertising. I will advertise my group. So we have different experimental techniques which are using to characterize materials. And for example, we have exact system, which allows us with single beam interferometer to measure piezoelectric properties. So this is for energy harvesting. Then you apply electric field or you apply tension and you see which current or voltage you are producing. And of course, to measure D33, all piezoelectric properties of material is possible. And also for ferroelectrics materials, and to those who do not know, ferroelectric materials are the materials which spontaneously polarizes, and the direction of polarization is possible to change with external electric field. So it's possible to measure hysteresis loops. And also in our lab, we have pulsed laser deposition technique, where you can make thin films. So it's real nanotechnology up to 20 nanometers or so. We have ultrasonic spectroscopy to measure ultrasonic properties, attenuation and velocity of the materials. And also another powerful tool which we have, it's EPR, electron paramagnetic resonance spectroscopy. And the difference from the electric spectroscopy is that the electric, when you measure interaction of external electromagnetic field with the material, you have the complex answer of the material. You cannot distinguish what's going on inside the lattice, inside the material. And EPR, when you measure a spin is very sensitive to surroundings, local surroundings. And due to that, you are getting information locally inside the lattice, what is going on, what structural changes with temperature are happening. And EPR, we have also ENDO, electron nuclear double resonance, ELDO, so we can do electron spin echo envelope modulation because it's pulsed method, which I will not go very deeply. And together with NMR, we can characterize what's going inside the lattice. And finally, and the most important part of my talk, so when you have a material and you want to use it for the cars or for mobile telephone or whatever, or for superionic batteries, you need to characterize it in a broad frequency range. So what we have is we are starting from impedance analyzer, which goes from 10 to -5 Hertz. So extremely low frequencies, extremely long wavelength. And as a physicist, I would say that no one experimentalist have a patience to wait so long for the results, because it will take about 1 week to get the reasonable result. So usually we are measuring from 10 to -3 Hertz, and this equipment goes up to 65 kilohertz, and the new one goes up to 1 megahertz. Of course, it's LCR meter, which is usual simple capacitance method, where you measure the capacitance, and from that you calculate the electric permittivity, real and imaginary parts. And then you use different vector network analyzers, which goes up to 110 gigahertz. And in this range, we use a coaxial line. And later I will tell why we use coaxial line only up to 2 gigahertz, up to here. Because due to high dielectric permittivity, you will face a huge problems, which I will explain a bit later. And then going to terahertz range, we use different waveguides. You see here, waveguide techniques. And further on, we go to quasi-optics, so tie domain or terahertz spectrometer, and Fourier transform infrared spectrometer, which uses the simple, I would say, quasi-optical methods, reflection and transmission. It's simple to measure. The most complicated part, which not many labs in the world are doing, is from 1 megahertz to infrared. This is a huge gap, and just I explained previously that this is the most important part now for electronics applications. That's where electronics is going into that frequency range today. So, measurement techniques. You have a vector network analyzer, you need to measure. So you have a coaxial line, output of the vector network analyzer. You have transmission line, you have free space, you can have resonant cavity. So the idea is very simple. You have a material under test, or in other words, if you have an object, you have incident line, which is reflected and transmitted. And from these two values, I think anyone is able to calculate the parameters of the material. So material under test, incident, microwaves or electromagnetic wave, reflected, transmitted, and to calculate. Then we should go back to Maxwell equations. And Maxwell equations are, as I already mentioned, it's true, it's working, but you have different boundary conditions, very different. So there are a lot of methods which are used to extract the parameters of the material in different configurations. So here in A, you have a coaxial line, inner conductor, outer conductor, and material under test, which you can place in the middle of coaxial line. And then measure, again, reflection and transmission. Another version, if you have ceramics or so, and you can make a ring of that, you can place it, a ring, in the coaxial line and again measure reflection and transmission. By the way, we used this method. We have a project with CERN, and CERN needs to measure magnetic susceptibility and the electric permittivity, because in Maxwell equations there are two parameters. It's a real and imaginary parts of the electric permittivity, so answer to electric field, and magnetic susceptibility or magnetic permeability also. It's the same, which is also changing the frequency. And they need to know exactly at gigahertz range the magnetic permeability. And this method is very good, but you need to make a ring. That's a shortage of this method. If you go to higher frequencies, it's really complicated. If you have a waveguide, you can close and measure the full cross-section of a waveguide. And again, measure reflection and transmission, and from that extract the parameters. The problem that for capacitors in electronics, as I mentioned, used barium titanate, and of course capacitors are better, smaller and bigger capacitance. This means that the electric permittivity must be as high as possible. And when you have a high dielectric permittivity material, this method is not working because, again, from Maxwell equations, it's very clear to see that you have reflection close to 1, transmission nearly 0. And from such data to extract material parameters is impossible. So another possibility is to make a needle-shaped sample and place it in the center of rectangular waveguide and then measure reflection transmission. And I will show how easy it is to calculate. Easy, I mean, you will see. Further on, it can be open space method, where you have antennas, transmitting, reflecting, and again, calculating. Also can be strip line, where you place the material and measure again reflection transmission. Also, it can be coaxial line, open-ended coaxial line, where you put the material at the end of coaxial line and try to measure. The problem or shortage of this method, of course, all these methods have pro and contra arguments, and they do not fit for all parameters, for all materials. And this requires a very good contact or very clean and very nice surface of a material. And of course, resonators, which is split posted resonator showed in the corner, where you can measure precisely the electric losses. So now a bit of arithmetics. We have a coaxial line. We have a material with high dielectric permittivity, and we need to know the properties. We would like to use it for 5G phone. We need to measure dielectric permittivity. So we have inner conductor of coaxial line, we have outer conductor, and we place our sample at the end of coaxial line. And the lines here shows the distribution of electric field. So it works like a capacitor. And the message, if you have such a capacitor, you cannot calculate it with simple capacitance formula, which you know from the school, I hope. But it's because it's higher frequencies, you need to use dynamical capacitor formula. What does it mean? It means that electric field in such sample, if you have high dielectric permittivity, epsilon, electric field is distributed not homogeneously in the sample. In simple capacitor or static capacitor formula, it is assumed that electric field is distributed homogeneously. When it is distributed not homogeneously, it goes like this electric field, and this is described by Bessel formulas. So such capacitance, this is we are going to such formula where electric field distribution, as I mentioned, is zero-term Bessel function, where K is propagation constant, the electric permittivity, magnetic susceptibility, and R is the radius of the sample at the end of the coaxial line. So this is first iteration, very simple. And then you calculate how should be the radius of a sample. Then we can go to the first maxima. This should be the radius, where we can assume that electric field is homogeneous in whole sample. In that case, radius of a sample is given by this formula, where lambda is the wavelength of electromagnetic wave, epsilon mu is the parameters of the material. And R should be less than this to have a homogeneous distribution of electric field. And we learned that, let's say we have 3 gigahertz frequency, then the electromagnetic field wavelength is 10 centimeters. And if we have barium titanate, which have more than 1000, let's assume we have the electric permittivity 1000 only, the radius of a sample should be less than 0.12 millimeter. If it's wider or bigger the sample, you will have non-homogeneous distribution of electric field, and simple capacitance formula will not work. So the results that you get will be fake, like fake news, which is now popular. For such simple arithmetics and such a small samples, to place it in coaxial line, it simply will not stand, because you must fix it with silver or platinum paste to have good electrical contact. It's complicated. So in that case, you need to have a sample holder, which is here. Sample holder makes life easier to place the sample, but makes more complicated result to calculate. In that case, if you look at the electromagnetic field and Maxwell equations, again, we have 3 different regions. And we must write electric and magnetic fields in all these 3 different regions. So that's written in the sample field. So inside material, you have electric magnetic field. Between the sample and sample holder, you have such an expression. And then you have boundary conditions, what I mentioned. It's nothing else as Maxwell equations, but you put the boundary conditions and you calculate the coefficients from these 2 equations, because electric and magnetic fields should fit together. If they do not fit, electromagnetic wave cannot propagate. So then you write for sample holder, again, boundary conditions. And finally, you are getting result for coefficients for sample holder, and so on. I will skip the arithmetics. And finally, simplified equation for the capacitance. Instead of simple equation that C is equal epsilon epsilon 0 as area of a sample divided by the thickness, you are getting such a nice and easy expression. Easy, I am cheating a little bit. It's not so easy. So simplifying, we have a dynamical capacitor method, which is expressed by Bessel functions. Is it working? Let's look. We have a vector network analyzer, our material under test, reflection, which is measured by vector network analyzer. And from this, we can calculate real and imaginary part of the dielectric permittivity. Let's have a look. If we use simple static capacitor formula, it's a black points, results at above 700-800 megahertz going up. This shows the formula. Is it true? the answer. It is not true. It is fake. It's due to non-homogeneous distribution of electric field, and we apply formula there in the place where we can not apply. It's not working. So dynamic capacitor with Bessel's functions shows a little bit better. You can extend by 100 megahertz or so, but not so much. So what is the reason for that? So now with powerful computers, it's possible to, with finite elements calculations, you can model and see what's going on. Of course, it's not applicable for the measurements, real measurements, but once to try and to check your model, it's very good. So what we did, it's a coaxial line, sample at the end, inner conductor, outer conductor, and try to calculate. So the lights show the strength of electric field, the color, and we see when we have small dielectric permittivity. So if to go back, firstly, we try to model somewhere in that region. And we see that we have excellent agreement and capacitor model is working. You see simply the color is the same. So electric field is homogeneous. If we increase slightly the electric permittivity, we can see here at the end that we have already different colors. So this is already distribution is not homogeneous. So we are getting the fake results. And if we increase further the electric permittivity, we can see that the picture of electromagnetic field is completely different. And here are the different modes generated inside the material. Even more complicated. Here again, another example, maybe better to see how electric field is distributed inside the sample. And even if you place a sample a bit not straight on the axis line, you can see that it's some rotating modes appear in this sample. So even dynamic capacitor model with Bessel functions, which I showed rather complicated, is not efficient, not working very well. So what to do? The idea is to separate. This part is coaxial line, usual mathematics, and the end, we should use another. So we go to, again, electric and magnetic fields to describe, and region A is a coaxial line. We write electric and magnetic fields. Then we use so-called term inhomogeneously filled circular waveguide. That's a circular waveguide where you have a dielectric material inside the circular waveguide. And this part, again, you should write electric and magnetic fields. And then the modes which propagate should fit each other. So it cannot be in one mode maximum of electric field, in another mode minimum of electric field. It should match. So mode matching becomes very important. And this is that they should be equal on the boundary between circular waveguide and coaxial line. So in that case, we are getting a bunch of equations, which is possible to solve numerically, no analytical solution. But finally, we are getting, I will skip mathematics. And you see here, hopefully you can see the points. So it's a dynamical capacitor, and black points is the what we call multi-mode capacitor. Then you generate different modes at the end of coaxial line with the sample. And this method truly works, and you can get the not fake, but real results. And example of PMN-PT material, which is one of the best piezoelectric materials, which are used in PCT, is used in ultrasonic medical equipment. So this is the same family searching for better piezoelectric, and you can see how the fake results differ from the real results of the electric permittivity and the electric losses in this material. The same method can be applied for, that was for reflection type measurements. The same method can be applied, you have inner conductor, sample, outer conductor, and this region is treated again as a cylindrical waveguide with the electric inside it, non-homogeneous cylindrical waveguide. And we can see points are calculated with finite elements calculations, and lines are measured and they fit very good. So we showed that this model is really working, and to get more information, I have not written it here, but our paper published in Review Scientific Instruments on that. And another interesting feature which I want to mention is that also, despite the fact that this is in the center, there is the maximum of electric field and minimum of magnetic field, this method is sensitive to magnetic susceptibility. And you can see reflection phase changes due to magnetic susceptibility also. So you can extract not only measuring simultaneously reflection and transmission, you can extract simultaneously magnetic and electric properties of the material. Even in this method, despite the fact that better method, what I showed was ring method in the coaxial line. So how much time I still have?
10 minutes.
10 minutes, okay, so I will speed up. Another is open-end coaxial line method, where very also interesting task, Agilent or now Keysight Technologies, they produce a probe for liquids, but the method which they are selling not accounting the boundary conditions of the liquid. So you need to have a huge quantity of liquids. But in science, usually you have sometimes sample very small quantities. So again, we used the same method, again, numerical simulations, and we see again that if we have a very limited volume, we have a different modes, different vibrations of electromagnetic field which are generated inside the probe. And due to that, we developed a method that's a magnetic field distribution, which is also interesting, also possible to extract magnetic properties. We developed a method which is 250 microliters. So few drops of liquid is enough to tell the electric properties, which is for ionic liquids, for biological substances, and we can measure up to 40 gigahertz. And calibration procedure, it's a short, open, standard liquid and unknown material to measure the properties. So that's shortly about waveguide. Now I will tell very shortly about waveguides. What I mentioned for ferroelectric materials, if you have fully filled cross-section, again, Maxwell equations and boundary conditions, nothing more. And electric magnetic fields in first, in second, in the material, in third, and again, boundary conditions matching, and you can solve reflection and transmission, and from that you can calculate the electric permittivity and magnetic susceptibility. Another method which is popular is the reactive load case, where you have a short and you change the position, and in different positions you are getting different reflections, and from that you calculate the parameters of the material. Also, full cross-section filling is possible to calculate the thin film's properties. If you place substrate, thin film, and you know substrate dielectric properties, you can extract from reflection and transmission the properties of the film. But as I mentioned, for PZT or barium titanate at gigahertz, its reflection will be 1. So in our lab was developed the method of needle-shaped sample placed in the waveguide, and from that to measure reflection and transmission. And again, because it's complicated stuff, I just show to know that mathematics is not so simple. Again, boundary conditions, Maxwell equations, cylindrical coordination system due to the sample shape, and the reflection coefficient looks like that with all these coefficients, and from that you can extract the parameters. And here is example at 10 gigahertz, radius of sample 100 micrometers, and you see how reflection modulus and transmission modulus are changing, and here we have resonance, and of course better to measure before resonance. So with such a thickness you can go only up to 1,000 or value of dielectric permittivity. So again, numerical methods to prove that our method is working, and it's working very well. And another thing which I would like to shortly, due to time limits, strip line, when we have electromagnetic wave propagating. Here is our sample, a coaxial line, and this method goes up to 12 gigahertz, quite well. So, example, BZN, barium, zirconium, niobate ceramics, and measured different methods. Simple capacitor, red, frequency range, coaxial line, yellow, sample connected between two coaxial lines, sorry, yellow, that's brown, and strip line, green, and we are getting the whole dielectric dispersion of this material. So it's not so simple, not so easy, but possible to extract. So waveguides I will skip, only to show that if you measure reflection and transmission, it's not only one solution. If you solve mathematically reflection, transmission, these formulas, you are getting where the green, blue, and red lines intersect with each other. These are the solutions. And from measured at 10 gigahertz, oh, sorry, 9 gigahertz, and you take only 10 modes, the same as we used in coaxial line multi-mode approach, we are getting the values which satisfy. So usually, I saw several papers where people are taking only the first value and claiming that this is the true. This is not a true. Again, due to multi-modes, you must know the static dielectric permittivity, and then from Kramer's chronic, you can evaluate which of these values are real imaginary parts are true. The others are purely mathematical solutions which have nothing to do with reality. And you cannot do application of a material, let's say with these parameters, thinking that your equipment will work in telephone or in radar. So due to the time limit, I will skip several examples and go only to interesting material, which is called artificial multiferroic, where you take PZT, which is ferroelectric and piezoelectric material, and cobalt ferrite, which is magnetic material. So the idea is to combine magnetic and ferromagnetic and ferroelectric material to have multiferroic, where you can switch the polarization with external magnetic field and the magnetization to switch with external electric field. So that's for memory devices, for example, can be used, and similar stuff. So the different concentration X shows the cobalt ferrite, and we see lead zirconium titanate, PZT, have a phase transition, nice anomaly, which is clearly expressed, but we do not see anomalies or contribution of cobalt ferrite. So what to do? First, we can look at the electric dispersion, and we can see very broad frequency range. We measured in terahertz, up to terahertz, the whole dispersion. So conductivity part, dipole part, and further on will be lattice part of infrared, but we stopped at that. And we have 3 different dispersions. And to explain such dispersion, you need to add conductivity part, you need to add relaxation part, and you need to add some soft mode with damping and so on, which goes in this part. So it's a damped oscillation, not a relaxation. And of course, you can get from these measurements all the parameters: contribution to the electric permittivity, relaxation time, damping, frequency, so all the necessary parameters which you need for applications. The same is barium titanate with nickel zinc ferrite, which I skip. But interesting thing that you need to extract the separate contributions, because you have composite. You have barium titanate and you have cobalt ferrite or another magnetic material. So there are different theoretical models. One of them is Maxwell, Wagner, Hashin, Stigman, and Brueggemann, and Lichtenegger. So we found that Lichtenegger is the best model, and we used to separate, and we succeeded, and we can see the contribution of barium titanate and contribution of nickel zinc ferrite in composite. So what is expected? Barium titanate have a phase transitions, which we can see here, and nickel zinc ferrite have no phase transition and goes in all temperature range stable. So shortly, conclusions. If you want in electronics to apply materials, you need to measure at high frequencies. And to measure in high frequencies, I hope you got a message. It's not so simple and easy. You must apply Maxwell equations, boundary conditions, and solve really not simple mathematical problems to extract the data. With that, I would like to thank you for attention, and you can see how electric and magnetic fields are going in the letters, in that geometry. So today, the finite element modeling, we used HFSS program, which allows to simulate, and depending on mesh, you can get very reliable results, but numerical modeling do not allow to do it quickly, because when you measure temperature dependence and you want to get 20 or 30 frequencies simultaneously, quickly on your screen, numerical modeling sometimes takes few days for one frequency, one temperature. So it's better to have analytical expression, which computer can do it immediately. So we tried to do that, and I think we are successful. So, and at the end, if you have some materials which are needed to be measured at microwaves, please contact me. Thank you very much.
Thank you. Maybe we have any questions from the audience? Okay, please. Just a minute, microphone.
Darius, this is Panayotis Flagos.
My name is Chandana. I am from KTU, Kaunas University of Technology. Thank you for the presentation. It's very interesting. My question is regarding impedance analyzer that you spoke about during the beginning of the presentation. Does it also measure the 31 mode of vibration for the material?
Piezoelectric, you mean?
Yes.
Yes, we can do it
Okay.
with exact machine.
Sorry?
We can measure.
Okay.
You asking D11?
Yes, D11.
Yes. So D11 is possible to measure by ultrasonic setup, which we have. Then you apply electric field and see what's going on, but it's a 10 megahertz frequency. If you need to measure it at a low frequency, so it's exact machine. Just I will show you. Oops. With this, with this one, then you can measure up to kilohertz. It depends because it's also frequency dependent. So you place the sample here, apply electric field, and with interferometer, laser interferometer, you measure the thickness.
Okay, so it can also measure D33 and D31 or any kind of
No,
nodes?
we can measure only D11 and D33.
Okay. Okay, and what would be the approximate cost of the machine? Just to know.
To buy it?
Yes.
It costs around, I think, something 150,000. It's not very expensive.
Okay. And also another question is regarding the material that you spoke about, cobalt ferrite with PZT.
Yes.
Is it possible also to measure piezoelectric property of that material? Any idea what could
Yes.
be the?
Yes. I have not presented here. I think in our paper, there are, which I showed again. I will do quicker like this. If you look at the paper, just a moment. Yes, Journal of Applied Physics. This is the link.
Okay. Okay. And any information about ferroelectric cellular polymers, not just PZT, but polymers also?
Polymer, PVDF?
Yes.
We have several papers with PVDF, but it was not the topic of my talk. So if you write email to me, I will find it and send the links.
Okay. Thank you.
What we did with PVDF and composites. We had PVDF with carbon nanotubes, with onions, and it's published.
Okay. And just another question about temperature dependence. Is a PZT material better than polymer when it comes to temperature dependence?
Good question. I do not know what to answer. What does it mean, better or worse? Which properties you need?
Which works better at higher temperature? Because
at higher temperatures, PZT works better, I think. PVDF polymer is not so good.
But what about the PP foam or any other new kind of ferroelectric cellular polymer, which is having the foam structure?
If they polymers, if they remain stable, it's okay. But polymers have a bad feature that usually they do not survive high temperatures. High, I mean, so 500 Kelvin, so 200 Celsius or so on.
Okay.
So ceramics, in that case, ferroelectric ceramics is better.
Okay. Thank you.
Okay.
So thank you for the interesting presentation.
Thank you very much. Oh, surprise, surprise.
Thank you.